Thank you. Thank you for having me. So this one is not about the very recent one. This one is about some isoperimetric inequalities for the Hamming cube. Okay, so let me start with some definitions. We write QD for the D-dimensional Hamming cube. I guess you all know what it is, but for example, Q3 looks like this. So this is 0, 0, 0, 1, 0, 0, 1, 1, 1. So in general, QD is a graph whose vertices are binary strings of length d, and two vertices are adjacent if and only if they differ in exactly one coordinate. And let me remind you that QD is the graph product of QD minus 1 and K2, meaning that we have two copies of QD minus 1, and there is a perfect matching between them. So here we see two copies of Q2s, and there is a perfect matching. Okay? And in this talk, we write V for the set of vertices in QD. So the size of V is 2 to the D, and we'll use big N for this quantity. So big N is always the number of vertices in QD. And finally, we use mu for uniform measure on QD. So if A is a subset of V, then mu of A is just cardinality of A divided by big N. Okay? So nothing complicated. And so this talk is about some isoperimetric inequalities, meaning that something like this. So let's say we have a geometric object in general, and let's say V is its volume and S is its surface area. Okay, then so in this case, we can ask a question like this. Given the volume V, what's the minimum surface area? Right? And we ask this question on QD. So again, A is a subset of V. Then the volume of A is just the cardinality of A, but how do we define the surface area of A? You know, this is a graph. So, and there are usually we use two notions for the surface area: the vertex boundary and the edge boundary. Okay, so the vertex boundary of A is this, the set of vertices which are adjacent to A. And we write partial A for this vertex boundary of A. And the edge boundary is the set of edges between A and its complement. And we write nabla A for the edge boundary of A. Okay? Are there any questions? Okay, and there are some well-known isoperimetric inequalities in terms of those two notions of boundaries. First, we know that the vertex boundary is, the minimum vertex boundary is achieved when A is a Hamming ball. Yeah. So we know that Hamming balls have the minimum vertex boundary. On the other hand, the minimum edge boundary is achieved by subcubes. Subcubes have the minimum edge boundary. Maybe I just switched them. Okay. So for example, if mu of A is exactly a half, then partial A is at least what? So we can consider a Hamming ball of measure half. In this case, the size of the vertex boundary is just the size of the middle layer. So what's this? It's just some constant times n over square root of d. So in general, the size of the vertex boundary is always in the order, big omega of n over square root of d. Okay?
So when you say minimum size of the set?
Yeah, so given the size, so when we consider all of the sets of the given size, then yeah, thank you. And so if you have any questions, please ask it anytime. And okay, then how about the edge boundary? As I said, the minimum edge boundary is achieved when A is a subcube, especially in this case, when A is a half cube. So the picture is here. When A is a half cube, what's the size of the edge boundary? Don't be afraid, it's okay. Is n over 2 in this case. Okay. Okay, so these are some well-known isoperimetric inequalities on the hemicube. And for this edge boundary, actually there is some nice formula. So we know that in general, we know that the size of the edge boundary is at least A times. So this is for any measure, A times log n over size of A. And this inequality is tight, and the tightness is achieved when A is a subcube. So for example, if A is a codimension K subcube, meaning that measure of A is 2 to the negative K. In this case, when we have A, every vertex inside A has exactly K outside neighbors. So in this case, the size of the edge boundary is simply A times K, which coincides this bound. So, by the way, this is only true when mu of A is at most half. When A is bigger than half, then we can take the complement of A because they have the same size of the edge boundary. Okay, any questions so far? Okay, then let me state our result now. So we need a few more definitions here. We have A, so A is given. So in this situation, we define HA of X in this way. This is our A. So if this vertex X is inside A, then H of X gives the number of outside neighbors. So this is defined degree in V minus A of X if X is inside A. And if X is outside of A, we just assign 0 to this. So this definition is to capture the size of the edge boundary of A, right? Because we measure all of the outside neighbors for each vertex. And we use beta for this quantity, log base 2, 3 over 2, which is roughly 0.58. It looks strange, I know. But using this notation and definition, our main theorem says that. It looks more strange. Integral HA beta X d mu is at least 2 times mu of A times 1 minus mu of A, where this integral is just what you expect. This is defined summation for all x in V, HA beta X times mu of X. So this is just a natural definition. And because our mu is just the uniform measure, so this is simply 1 over n times the summation. And yes?
For what mu? Like for p bias mu?
Mu, this, uniform.
Okay.
Uniform measure.
Uniform.
Yeah, uniform measure.
Can you say again what the definition of d minus A is?
Oh, so this is the number of This is a degree in V minus A of X. So this is the number of neighbors of X in outside of A. Okay? So I know that this inequality looks quite strange at first glance. So let me compare this expression to this usual one. So when we consider this without beta, what's this? Yeah, exactly. So this is simply nabla A divided by n. So this is just a usual edge boundary. And we know that this has some tight lower bound, which is stated over there. So using this notation, we can write the lower bound is mu of A times log base 2, 1 over mu of A. Of course, this is for mu of A is at most a half. And mu is bigger than a half, it's just symmetric. Yes?
What happens if you choose the obvious Hilbert to lower bound? You take a little bit of power. What do you get as the lower bound?
I'm sorry?
Like, you get something worse if you just use the obvious, use that and use Hilbert to lower bound to the left-hand side of what's in your main theorem, right? You get something that obviously is worse than what you prove. So what do you get?
I haven't tried it.
Okay.
Yeah, but this bound is tight, and I'm not sure what we get from your idea.
Okay, and other exponents other than beta, do you know anything? Or?
Yes, I'm gonna say that.
Okay.
Yes, thank you. Yeah, thanks for your question. I'm gonna talk about that.
Is this supposed to be replacing the one on top, but you got a stronger?
Which one? Oh, I mean this one?
Yes.
Compared to this, they are the same thing.
They don't look the same. There's an n instead of a log.
Oh, because I'm using this integral, so it's divided by n. In this case, this is simply n over size of A, right? Because mu of A is here.
Normalization, mu divided by n.
No, I understand. How's the n coming out of the log?
This is log. Oh, so mu of A is just size of A divided by n. And we have the n here. Yeah. Thank you. Any other questions? I know it looks strange, so please ask me questions. Okay. And yes?
When does equality go?
You mean for this one?
Yeah.
We'll get there. Be patient. We'll get there. Thank you. Thank you for your questions. Okay. And at least I can say that. So this inequality is tight for all the subcubes. So which means all the measure 2 to the negative power. Oh, okay. So the next thing is the tightness about this inequality. This is tight. Let me write here. So our main theorem is tight when mu of A is a half and a quarter. Oh, thank you for the reaction. Okay, so for example,
I was just agreeing
I think I should record this lecture, this talk. When A is codimension 1, let's check. When A is codimension 1 subcube, then the left-hand side of our main theorem is just integral 1 d mu, but the support is A, right? Right? And so this is just mu of A, which is a half, and this is equal to the right-hand side. And when A, please allow me to do this, when A is a codimension 2 subcube, then the left-hand side is the same, but what's the integrand in this case? This is the place where beta comes in. So we know that HA of X is 2. But when we raise this by beta, we have 3 halves. So what we have is 3 over 2 times 1 over 4. This is the measure of A. And we have 3 over 8, which is equal to the left-hand side. So our effort was to make that inequality tight, and that's why we had to use some strange beta over there. Oh, yeah, thanks. Yeah, I mean, it's right. Yeah, right-hand side equal to right-hand side. Yeah. anyway, so our result is tight in two ways. Meaning that first, we cannot improve 2 in the right-hand side, the constant 2, right? Second, we cannot improve beta in the left-hand side. So beta is the best possible exponent, which makes the inequality tight and true. Okay?
Well, I mean,
Yeah, of course. I mean, so.
He was like 1 more time than you improved.
Okay, so.
I'm sorry.
It's okay. Thanks for making my talk fun. So, okay, so actually at the beginning we had some specific problem that motivated us to prove that inequality, but we'll see that at the end of this talk. But for now, let me introduce what inspired us to have this form of the inequality. That's due to Talagrand. Let me use that board. So Talagrand in 1993 proved this integral square root of HA d mu is at least 2 times square root of 2 times mu of A times 1 minus mu of A. So this looks very similar to our main theorem, but the proofs are very different. So we didn't use the same idea. And let me make some remarks to have better understanding on this inequality. First, in this inequality, mu is actually the product measure, mu p. So this is the product measure. So in this formulation, square root of 2 is actually some expression in p. But when p is a half, then that expression gives us square root of 2. And second, this inequality is not tight. So for example, when A is a codimension 1 subcube, then we know that this side is a half, but this side is only square root of 2 over 4. So this is not tight, but this inequality is tight up to constant. So when we plug in when A is a subcube or a Hamming ball, then this inequality is tight up to a constant. And also, but to be fair, let me say that Talagrand didn't care about the tightness, because what he concerned was this. He wanted to show that the trade-offs between the vertex boundary and the edge boundary. Let me say a little bit more about number 3. So when we apply Cauchy-Schwarz in this expression or here, then what we have is, okay, let me call the right-hand side star. And what we have is star squared is at most mu of some kind of vertex boundary of A times integral HA d mu. So this is the right definition for this one is the inner vertex boundary of A, meaning that when we have A here, then inner vertex boundary is the set of vertices which had some outside neighbors. So this is indeed the vertex boundary, but it's located inside of A. And this is what we know. This corresponds to the size of the edge boundary. So what that says is that the product of the inner vertex boundary and the edge boundary is bounded below by some quantity which does not depend on D, the dimension of the Hamming cube. So it only depends on some expression in P and the measure of A. And before Talagrand, there was a result by Margulis. And what he showed was exactly this. This expression is bounded below by some quantity which does not depend on D, which only depends on P and the measure of A. And so what Talagrand concerned was the quantification of the result in Margulis. And that gives us this tight lower bound. Tight means tight up to constant. Tight lower bound for the product of this expression. So let me give you some more example. So for example, if A is a Hamming ball, then we know that it has the smallest vertex boundary. But how about its edge boundary? Huge, right? So there's some trade-off. On the other hand, if A is a subcube, then we know that it has the minimum edge boundary. But how about its inner vertex boundary? It's the maximum possible, right? Right? Because in its inner vertex boundary is everything. Yeah. And what it says is, whatever A we have, we cannot do better than this, because this inequality is tight up to constant. So this is what's in Talagrand's inequality. But as I said, our motivation is quite different. But eventually, it gives some application on this trade-off between vertex boundary and edge boundary. Okay, any questions so far? Yes?
So can you like interpolate between, I mean, if you take like a Hamming ball and cross it with it, take the direct product with some subcube, do you get some sort of tightness here in the whole regime as you can, you lower one, you raise the other one. Can you get that, or like for any vertex boundary, edge boundary, the product is at least a constant times that thing?
I mean, so actually, I thought about something like this. So what if mu of A is a quarter, and we take A, this part. So this is QD minus 1, but we take the half Hamming ball of this subcube. Then maybe it gives us some other tightness for that inequality. But I'm not sure if we have the tightness for some like arbitrary structure. You can try it. I haven't tried it so hard.
I think someone told me once.
Okay. Anyway, so as I said, okay, done. So as I said, we needed tightness. So we had some specific motivation, and we needed tightness. So let me get back to our work. So we needed tightness. When mu of A, in particular, when mu of A is exactly half. So the first thing that we tried was to see if we can replace this by 2. If we can do this, then this inequality is tight when mu of A is a half. But we know that this inequality is not true, right? Because as I said, we have beta here, and this beta is best possible. And because a half is smaller than beta, which is 0.58, so this inequality cannot be true. So what we did was quite a lot of experiments. So we tried many candidates for this, in particular for the exponent, and we tried many expressions for here. But most of them are either not true or impossible to prove. So as I said, our main theorem was the only thing which is tight, true, and possible to prove. So yeah, that's why we are here now.
Do you have one that was impossible to prove but you think is correct?
Maybe we can show like. So this is motivated by the. We have this. So maybe we can show that. And log base 2 1 over mu A to the beta, when mu of A is at most a half. And this is not true when mu is bigger than 1 over 2, when mu of A is larger than a half. So what we tried was maybe we can put some other expression here. So we think about this hybrid version of inequality, but this is the thing that's impossible to prove. Because, So because our proof is basically induction on D, and when we have this hybrid version, the induction is just too complicated. So we couldn't do it, but you can try it. I'll be very happy to see some more tight inequalities. Anyway, so as I said, the proof of our main theorem is basically induction on D. But I decided to skip this in this talk because I think it's better to use our precious time on seeing the applications. So we'll focus on some applications of our main theorem. But I want to point out that our proof is quite elementary, meaning that we really didn't use any heavy machinery. It's just quite basic argument, like some shifting or, yeah, that's it. And I think this is a nice point of our proof because this means we can show some interesting applications only with these elementary tools. Okay, so so let me move on to some applications. And are there any questions before that? Okay.
Can I ask you again about this? Can you explain again this bound star squared?
You mean this? Oh, yeah, so this is the inner vertex boundary of A, meaning.
Where does it come from?
Oh, it's because, so inner vertex boundary is the support. So inner vertex boundary is the support of this function, h of A. So this is actually square root of HA times 1 of support, HA. And then we just use Cauchy-Schwarz. Okay, any other questions? Okay, the applications. Okay, the first application is separating the cube. So it's more or less in the same spirit of this, the trade-offs between vertex boundary and edge boundary. And for now, we assume that mu of A is a half. Okay, and so our goal is to separate, so given A, our goal is to isolate A by removing some vertices and some edges. So for example, partial A is the set of vertices that we have to remove to isolate A, right? And nabla of A is similar. This is a set of edges that we have to remove to isolate A. Okay? Then one natural question is, what if we are allowed to mix the edges and the vertices to isolate A? So what if we mix the vertices and edges? And let me state our conjecture first. Conjecture, let me call this 1. Conjecture 1 says that there exists some universal constant, k, bigger than 1, such that, let me give a name. So let me call this set W and this part B, so that V is the partition of B is partitioned into A, B, and W. Is this situation clear? So W is the set of vertices that we want to remove, and then we'll remove nabla AB. And our conjecture says that nabla AB plus some constant times scale root of D times size of W is at least n over 2. Oh.
So this is for every set of measure half?
Yes. So this is our conjecture, which means we don't know it's true. And so do you see some motivation of this conjecture? So for example, if we decide not to use the vertices, then this is just vertex boundary of A, right? And in this case, vertex boundary of A is at least n over 2. And if we decide, oh yes, yeah, edge boundary, thank you. And if we decide not to use any edges to isolate A, then this W contains the vertex boundary of A. So this inequality is true. And what we claim, what we conjecture is, no matter what W and B we choose, we cannot do better. Okay, so this is in the same spirit of this trade-offs, but somewhat different because this here, nabla AB, and when we mix nabla AB and W, they are not exactly vertex boundaries or edge boundaries, but still, to isolate A, we claim that we cannot do better than that. Okay.
Yeah, so you can't, like, you can't hope to write down, this is true, this is that, right? Up to.
If this is true, yeah,
Okay.
yeah, of course. And the
I mean,
tightness.
like, even in between, I mean, you know, for all.
For all of the structures, you mean?
For W, for W being, for all vertices and all edges, but like for half vertices and half edges, would this also be tight? If it's
I think it's not constant, but we need some tight thing. I mean, so here this is, so because we have K, so this part is quite loose. But we'll see some ultimate version of this conjecture.
okay.
Okay, so this is still open, but our main theorem easily gives this weaker version. We can do this, nabla AB plus d to the beta W is at least n over 2. And this implication is very simple. This is just one line, so I'm going to show you that right now. Proof. So to get this, what we do is to apply our main theorem. Is this here? No? I think I should keep our main theorem somewhere. So our main theorem is integral HA beta d mu is at least twice mu of A times 1 minus mu of A. And we apply that inequality for B union W and see what happens. And because of our assumption, we know that the measure of this set is exactly a half. So that means by our main theorem, this is bounded below by a half. I just plug in a half to our right-hand side. Yes. Ooh, oh, I'm sorry. Yeah. Okay, so I should jump into the hole. Okay, and this is equal to, so we can separate this into two parts, B and W. Oh, sorry. Yeah. Right? So we consider the edges separately. And then what happens? For this part, this is at most, so this inequality is only for this part. This is at most integral B H B cup union W d mu. So I just removed beta. We can do this because x to the beta is almost at most x for integer x's, if x is an integer. And h is an integer valued function. Okay? And what's this? This is our support, but we only consider this on B. So that means this counts the number of edges between B and A. We don't care about the edges here. So that's exactly nabla AB divided by n. And this part will handle the edges between A and W. So for this one, we know that this is at most d to the beta, because this is the regular Hamming cube. And so the entire expression is this times mu of W, which is d to the beta, this beta times W divided by n. And we are done. So this is really one-line proof and simple modulo this main theorem. And as I said, our main theorem is quite elementary. Not easy, but the tools are very elementary. So this is nice. Anyway, so this is the proof of this statement. And let me state some ultimate version of our conjecture. So conjecture 2 says that we need some more definition. We define this for the minimum size of the vertex boundary, where the size of A is exactly A, and nabla A is the minimum size of nabla A, where the same. And yes?
So you're saying your main theorem is tight, and it implies the conjecture just with a different beta, right?
Oh, yes.
So why do you think this beta can be improved?
Okay, so one way to prove this conjecture is to prove this with this replacement.
I see. Okay.
So in this case, so as I said, this inequality itself is not true, but we still suspect that this inequality is true when mu of A is close to half. But we don't know how to do this. But if we have that, then this implies this without K. Yeah. Okay, any other questions? Okay, so with those two definitions, our conjecture 2 says this. If the size of A is A, then nabla AB divided by nabla A plus partial size of W divided by partial A is at least 1.
So they should be capital or
Where?
in the denominator?
In the denominator, what?
Capital?
The definitions are for small a, the size.
Sorry.
Yeah.
Oh, yeah.
So for all of the sets of size A, we conjecture that. So we know that this inequality is tight when W is empty set or nabla AB is the empty set. And we claim that even if we mix the edges and the vertices, we cannot do better than this. However, this conjecture is not true. I figured it out this morning when I was preparing for this talk. This is why we should give a talk. But there is a silly counterexample when A is okay, so my counterexample happens when A is this. So, but I think this is kind of like a pathological. Okay, let me take it back. We still conjecture that this is true when A takes some reasonable value. For example, when A is 2 to the negative power, or mu of A is 2 to the negative power, then in this case, a subcube is a tight example for this one. So we conjecture that if the value of A is quite reasonable.
For an integer k, what does that mean?
Oh yeah, for integer k. So thank you. So when so for integer k, when 2 to the negative, so when we have this 2 to the negative power, then that means the minimum edge boundary is always achieved by the exact subcubes. So in this case, we still conjecture that this inequality is true. And yeah, we think this is very nice, beautiful conjecture, but for now, this is out of reach, and we don't know how to do this. And do you see that? So we see that this is stronger than conjecture 1, because here we do not allow any constant. So we require the exact size of this vertex boundary and the edge boundary. Okay, so this is the end of application 1. And are there any questions?
Do either of these conjectures mean anything for that side?
I'm sorry?
Can either of these conjectures tell you something about the question there?
You mean which question?
You wanted to prove mu of A is roughly half or something like that.
Oh, this. Oh, so as I said, if we can replace this by 2, then it implies conjecture 1. But for conjecture 2, to have conjecture 2, we need exact tight inequality also for vertex boundaries. But this does not give us a tight bound for the vertex boundary.
Second, you go backwards.
Go-
If you do conjecture 1, conjecture 2.
Ah. Yeah, probably. I haven't thought about that. So let's say if conjecture 1 is true, then does that imply Talagrand? Square root of h. I don't know. I have to think about that. Maybe we can do this later. Okay. Any other questions?
If conjecture 2 is false, then it certainly implies that.
Yeah, thank you. But that's for what our concern is for the 2 to the negative power, and we don't know if this conjecture is false. Yeah, thank you. And any other questions or comments? Okay, then let me move on to our second application, which is again nice. So finally, our second application shows us what our original motivation was. And so our original motivation was to prove this theorem. The number of maximal independent sets in the Hamming cube QD is asymptotic to 2 times d times 2 to the n over 4. And I know that this quantity, again, looks quite mysterious at first glance. So let me give you some more background. Oh, by the way, so this is going to be a little bit of digression. But I think this topic is quite interesting, so I want to spend some time on this topic. Okay, so this quantity is actually an easy lower bound for this size of, for the number of maximal independent sets in QD. So let me show you the construction for the lower bound. Okay, so this is about the lower bound. It's gonna be fun. So we know that, let me remind you that QD is a graph product of QD minus 1 and K2, meaning that we have 2 copies of QD minus 1, and there is a perfect matching. Okay? And because QD minus 1 is again a Hamming cube, so some vertices are even. Here square means even vertices in the half cube, QD minus 1. And some vertices are odd. Should I define what even vertices are? So these are the vertices with even number of 1s in its coordinates. Okay, and this is odd. Okay, then let me collect. Oh, by the way, because those 2 copies are isomorphic, so the other ends of each edge has the same parity, like this, right? Then what happens when we collect all of the even edges? First of all, this forms an induced matching. Meaning that this is an induced subgraph, which is a matching. In other words, this is a matching, and there are no edges between the vertices.
I'm sorry that I'm confused.
Oh.
You have an even vertex.
Uh-huh.
You have an edge.
Yes.
No, it's
Oh.
even in QD minus.
Yeah, even in QD minus 1.
Thank you.
Yes.
Okay.
Okay. Is it better now? Okay. So we collected all of the even edges, and then it forms an induced matching because this is an independent set. Okay. Okay, then what's the size of this induced matching? n/4, right? Because this is a half cube, so size is n/2, and we collected half of the vertices, so its size is n/4. Now let me make some notes. First, this n/4 is the maximum size of an induced matching in QD. Second, this is another, so those are easy facts. Second, this is more interesting. All of the maximum induced matchings are gotten by this construction. So here, this means this. We choose one way to decompose for this decomposition, and how many ways of decompositions are there? So this is the Hamming cube of dimension d, so there are d directions, so there are d ways to choose this decomposition, and then we choose one parity. And I claim that, this is an easy fact, I claim that all of the maximum induced matchings are gotten by this construction. So there are exactly 2 times d of the maximum induced matchings in the Hamming cube. Okay, and so in our paper, we call this canonical matchings. So we call those maximum induced matchings canonical matchings, and there are exactly 2 times d of them. Okay. Then there is a trivial way to construct maximal independent sets from an induced matching. What's that? We can choose, one vertex from each edge. Then this forms an independent set. Then we can just add some more vertices to make it maximal. So in this construction, we have at least 2 to the n/4 maximal independent sets, right? And again, this is an easy exercise. This is actually equality, which means each extension is unique. This is another easy exercise. So we have this many maximal independent sets from each canonical matching, and there are exactly 2 times d canonical matchings. So that gives us an asymptotic lower bound. So from here, we have at least 2 times d times 2 to the n/4 maximal independent sets. So and here I used this because there are some overlaps between the maximal independent sets gotten by different canonical matchings, but they are the overlaps are negligible. So this is a lower bound, and our main task was to show that this trivial lower bound is actually the truth. That was everything about our work. Okay. And let me make some remark. So that theorem is actually not just about the numbers. This is actually about the structure of the collection of maximal independent sets, meaning that, let's say this is the collection of all of the maximal independent sets in QD. Then what this theorem says is there are exactly 2 times the phases. And in each phase, this consists of the maximal independent sets gotten by that construction from a certain canonical matching. So in each phase, there are exactly 2 to the n/4 maximal independent sets. And so it says this is everything. I mean, asymptotically, this is almost everything. So it says that the structure of this collection is nice and clean. And compared to some other results in the same field, it's quite strikingly nice and clean, meaning that, so we know that counting independent sets or counting graph homomorphisms is a big topic, and there are quite a few results in this asymptotic enumeration in the Hamming cube. So for example, yes?
All maximum independent sets occur in something like
No, asymptotically. So the precise statement is the number of maximal independent sets not gotten by this construction is negligible.
I see, but would they fall into these 2D phases?
I don't understand what you mean by follow this.
No, I mean, you said they all have this 2D phases.
Oh, you mean this collection?
Yes.
Asymptotically. So there are some negligible portion of this collection. So those are not in these 2D phases. So asymptotically, yeah. So for example, Korshunov and Sapojenko in 1980s showed that the number of independent sets in QD is asymptotic to 2 times square root of e times 2 to the n over 2. So it has e term, some mysterious e term here. And actually 2 times 2 to the n over 2 is a trivial lower bound for the size of this collection. Do you see it? Because QD is bipartite. So and each part is size n over 2. And we know that every subset in this part is an independent set. So from this part, we already have 2 to the n over 2 independent sets. And because we have 2 parts, so we have 2 here. But what this says is that there are more independent sets. So this extra e term corresponds to kind of like impurity in this collection. And something similar happens to counting the number of colorings. For example, 3 colorings, there are some results on 3 colorings, 4 colorings, and
What do you mean impurity?
yeah,
Between 2 copies of QD minus 1?
no, let me, so in this case, this impurity means not exactly inside one part, but here, and it has some extra elements here. So this is not exactly pure configuration. And the contribution of those impure configurations is not negligible. It gives some significant contribution. And something similar happens to like counting colorings, but that doesn't happen in this case. So the structure is very nice and clean. Okay, so this is the end of digression, and I'm ready to go back to our work here. Yes?
Why is there no G factor here?
Don't worry about it.
I'm sorry, what?
Why is there no G factor?
Oh, because we only have two parts. So here we have 2 times D phases. So
Okay, but I mean, you could just take another way to decompose QD.
no, the bipartition is unique.
Oh, sorry, yeah.
Yeah. Thank you for the question.
Right, okay, sorry, okay.
Yeah.
Not that backward, okay.
Any other questions? Okay. And do I have only 5 minutes? Oh, it's too bad. So I think I should skip some.
You can take your theorem.
Really? Thank you. But let me make it short. I mean, shorter than what I planned.
We've interrupted you a lot.
So let me skip this slide. Directly move on to the point, get to the point. Okay, so as I said, our original motivation is that theorem, and that's quite hard. And it took us 2 years to finish that. So naturally, we had a lot of obstacles. And one of the obstacles led us to prove our strange that inequality. And so then, so we had this obstacle. How do I spell obstacle? Obstacle. And let me point out that this one is not even one of the largest obstacles, because as I said, this work is quite easy. Anyway, this mysteriously led us to this situation. So let me skip the connection. This is not so trivial. I mean, this connection is not so immediate, but let me skip it because of the time constraint. So our situation was like this. Let me draw out the familiar picture, A, B, and W. So V is partitioned into A, B, and W. And our situation was, first, mu of A and mu of B are close to a half. So this means 1 plus little o of 1 times a half. So this naturally means mu of W is very small. It's little o of 1, but not terribly small. we had this one is much larger than 1 over d. This means that we cannot ignore the contribution of edges coming out from W. This is the irregulars. And finally, we had nabla AB is close to n over 2. I know, so I'll say a little bit more, but yeah, for now, please bear with me. Our question was, in this situation, can we say that A is close to a subcube? Yeah, it looks, let me say a little bit more to have some more feeling about this situation. Why do we ask this question? Okay, here comes a little bit about the background. Compare this question to this case. If there is no W, if there are only A and B, then that question is about the stability version of H isoperimetric inequality. Meaning that our question looks like this. If nabla of A, we know that this is at least A times, right, log n over A. Then if this is close to this minimum, A times log base 2 n over A, does this mean that A is close to a subcube? Here close is defined by the symmetric difference. Does this question make sense? So the other direction is trivial, right? If A is close to a subcube, then naturally it's the size of the edge boundary of A is close to the minimum. So this is stable, and we are asking the other direction. This question is studied, quite seriously studied. So there are many results. For example, Friedgut, Kalai, and Naur first proved that this direction, this implication is true when mu of A is a half. And after that, Bolobash, Lieder, and Riordan proved that implication is true when the measure is this and this. So it was kind of like some gradual progress. And finally, David Ellis proved that implication is true for any measures. So, but as you see, it was not an easy work, and their proofs are all based on some Fourier analytic method. For example, Ellis, his argument is based on some theorem by Talagrand, but this Talagrand is not that Talagrand. This Talagrand implies
The Talagrand is the same.
this Talagrand theorem is not the same as that Talagrand theorem, but this theorem implies KKL. So Kan-Kalai lineal. So here you see some flavor of this direction, right? So it has to do with some argument on influences, something like that. Okay, so it was a hard question, and I want to say that our situation is trickier than this because of that W. Do you see the connection? So if we did not have W, then our question is exactly here. But because we have W, so what's the matter? So what's the problem? Because we have W here, so we cannot necessarily assume that nabla of A is small. So in our situation, the difference is nabla of A is not necessarily small. And it was our main obstacle. So then how do we prove? Yes?
What W could you be worried about? Like Trapp's functions? I mean, it looks like this can't happen, right? I mean,
You mean, what do you mean by what W do we
I
worry?
mean, there's this small set W, and that, if you take it out, then A to B are
There will be many edges going from A to W.
So,
yeah, it would be like what?
so this implicates this question.
But you think this can't happen, right? I mean,
Yeah. So I will show you this now.
Okay.
Thank you. Okay, so for this question, the answer is no, not true. A is not close to a subcube. So of course, the answer depends on the quantification. And the answer is no if mu of A is as large as big omega of 1 over square root of D. Why is that? Because we can choose W as the middle layer. And let this A, let this B. Then there are no edges between A and B. So this situation is true, but still A is by no means close to a subcube. So our conjecture, naturally, was that this is the only obstacle. So our conjecture was, the answer is yes, if mu of A, mu of W, is little all of 1 over square root of D. But we don't know if this is true. But what we have is our main theorem implies the answer is yes if mu of W is big, little of, guess? Any guess? Yes, our old friend beta. So I think so this conjecture looks so natural, but it was so frustrating that we could not prove that. But instead we have some weaker result.
What kind of closeness to the subcube do you need for that?
I'm sorry?
What are you looking for when you say A is almost a subcube?
Oh, yeah, so this is defined by symmetric difference. So this means there exists some subcube C such that the symmetric difference is little of n.
Okay.
Yes?
So does this end up giving an elementary proof of FKN? Or
FKN? What's FK?
you wrote that earlier.
Exactly, yeah. So that's one of my remarks.
Nice.
Yeah, nice. As I said, this elementary argument gives a nice result. So there are a few remarks. First, as Ryan pointed out, our result implies FKN here, right? In a stronger way. And second, actually our result gives something stronger, meaning that our result covers mu of A a quarter because of the tightness. So here we assumed A is of measure half, but even in the case measure of A is a quarter, we can get something similar. And this means, so 2 means that our result implies FKN and the half of BLR. So we cover this case. So one natural open question is, can we tighten our main theorem for other measures? So as she asked, so we have some candidates which is impossible to prove, but once we have some inequality or a family of inequalities which are tight for some other measures, then it will give us those other cases in a stronger way. Okay. Okay. So finally, should I finish now, or if you are curious, I can show you a sketch of this implication. But if I run out of time, then I can finish now. So maybe I can finish now, and we can talk about the proof. If you are curious, then we can talk about the proof. Oh, really?
How long is it?
It's just one slide. Okay. Yeah, these are slides. So this is a very rough sketch. So we have assumptions, and what this says is that the average degree from A to B is 1, right? And when we apply our main theorem, we can actually show that it's not just about the average. We can show that for almost every x in A, degree in B of x is 1. This is where we used our main theorem. And then, once we show this with some different argument, we can show that almost all edges in nabla AB are in the same direction. This is not trivial. It needs some argument, but this is just a sketch. And finally, from here, we showed that A is close to a subcube. Again,
It's almost the same, or?
no, this is not trivial because this can imply that we have, so this is the fixed direction with what this gives. But it's possible that A, B, A, B. And because we have that W, so W can be here, and here. So this picture, it's not immediate to see that this picture is impossible. And for this implication, again, we needed the main theorem. But for this one, it's somewhat different. Shifting and Harris, like some elementary combinatorial argument. And yes, so this is it. And I can.
We say a little bit more about this.
Okay. So which one? Okay, so for this one, it's similar to what I did somewhere, but let me show you. So that's again, that's one line, so I can show you the argument. So using assumptions, we apply, okay, so the picture is this. And what we do is to apply our main theorem on A union W this time. And here, because measure of W is negligible, so this is again close to a half. And we do the same trick. Compute this on A and on W. Okay, so let me do this part first. For this part, it's going to be eventually d to the beta times mu of W at most, right? We do something similar before. What's this? Negligible, because of our assumption. And for this part, so this is almost at most integral A, H, A union W d mu. I just ignored beta. This is on upper bound. And this is nabla AB divided by n. Yes, so which is by assumption at most a half. What does it say? It says that all of the inequalities are tight. So that gives this one and this one is close for almost every axis, almost every x, right? So and what does it mean by this is equal to this? 1 or 0. But it cannot be 0 because of this lower bound. So it says that almost every x, for almost every x, degree is 1. So as I said, yeah, this is an easy computation, but quite nice. And for this one, yeah, as I said, this is some combinatorial argument. So we used some shifting argument to say that we may assume A is increasing and B is decreasing. And once we have an increasing set, an increasing family, then we can apply Harris. So we made a contradiction for, so we assumed, so if there are two different directions with significant contribution, then we can make contradiction using Harris.
Is that your integral of h of a union w, and then you say
Mhm.
is equal?
Uh,
Is that less or equal to, or like, how does W disappear and C appear? Yeah, that and the line below.
because we are considering this on A. I mean, so here we already ignored this, the second integral. And this one is equal to this.
Okay.
We don't have beta here.
Okay.
Is that right? Because this is on A, so we only consider edges between A and B. We ignore this. We don't have to, I mean, we ignore this.
Okay, because H is defined with you. Okay.
Yeah. And finally, yeah, let me skip the last part. This is, again, some similar argument using the main theorem. And this is the end of the proof. So as I said, when we apply the tightness for measure a quarter, then we follow some similar argument, but we do need some extra argument, but basically similar to get A is close to a subcube. Okay, so this is all for today, and thank you for listening.